This week's lesson is probably more demanding than the previous week's lessons. The next 2 weeks we will be performing some basic math to get a better grasp of the statistical concepts that infuse assessments. Don't panic, as I've really strived to walk you through each step as simply as possible. I do encourage you though to find a quiet place to work free of distractions. What we are going to do today is not hard, but it does require concentration. The learning objectives are as follows. Understand the concept and utility of descriptive statistics. Identify and describe 3 measures of central tendency. Develop the skills to construct a frequency distribution table. Develop skills to compute standard deviation. And understand the basic properties of a normal curve. Descriptive statistics is the term given to the analysis of data that help describe, show, or summarize data in a meaningful way such that patterns might emerge from the data. Descriptive statistics do not allow us to make conclusions beyond the data we have analyzed or reach conclusions regarding any hypothesis we might have made. They are simply a way to describe the data. We use descriptive statistics to make small and large decisions in our everyday life. The most common descriptive statistic is the mean or average. I'm in the process of buying a house in the area, and I have been looking at the average or mean home price to make decisions about if I can afford to live in the area or if I'm paying too much. Later in the lesson, I'll briefly mention a couple of inferential statistical measures, Pearson correlation and regression. Unlike descriptive statistics, inferential statistics do permit us to make scientific claims about the relationship between 2 or more variables. Let's start with the easiest variable, nominal variables. Nominal scales are used for labeling variables without any quantitative value. Nominal scales could simply be called labels. Here are some examples below. Notice that all of these scales are mutually exclusive, so there's no overlap and none of them have a numerical significance. A good way to remember a nominal scale is it sounds like name, and nominal scales are kind of like names or labels. Examples of nominal scales are eye color, hair color, where do you live, what is your marital status, what is your religious affiliation, what is your occupation, in what country were you born, what's your astrological sign, to name just a few. With ordinal scales, it is the order of the values is what's important and significant, but the difference between each one is not really known. Take a look at the examples below. In the case of a Likert scale, we know that very satisfied is better than satisfied, but how much better is it? For example, is the difference between okay and unhappy the same as the difference between very happy and happy? We just can't say. Ordinal is easy to remember because it sounds like order, and that's the key to remember. With ordinal scales, it's the order that matters. But that's all you really get from these. You really aren't supposed to calculate a mean based on ordinal data. It's okay to get a median. We'll talk about that in a minute. But if you see any statistical analysis which use ordinal data and they calculate a mean, that's kind of a no-no. So interval scales. These are numeric scales in which we know not only the order, but also the exact differences between the values. Like the others, you can remember the key points of an interval scale pretty easily. Interval itself means space in between, which is the important thing to remember. Interval scales not only tell us about order, but they also tell us about the value between each item. The classic example of an interval scale is temperature, because the difference between each value is the same. For example, the difference between 60 and 50 degrees is measurable 10 degrees, as is the difference between 80 and 70 degrees. Interval scales are nice because the realm of statistical analysis on these data sets opens up. For example, central tendency can be measured by mode, median, or mean. Standard deviation can also be calculated. Calculators using interval data, however, are limited, as interval data does not have a true zero. While you can add and subtract interval data, you cannot multiply it. I can imagine you're thinking, what is she talking about? This can be a tricky concept to grasp. 80 degrees is not twice as hot as 40 degrees, because there is still heat in the air at 0 degrees. Think about Fahrenheit. It is a user-friendly measurement of temperature, but 0 degrees is an arbitrary scale. Heat's still in the air at 0 degrees. ratio scales. Ratio scales are the ultimate nirvana when it comes to measurement scales because they tell us about the order, they tell us about the exact value between units, and they also tell us about absolute zero, which allows for a wide range of both descriptive and inferential descriptives to be applied. At the risk of repeating myself, everything above about interval data applies to ratio scales, plus ratio scales have a clear definition of zero. Good examples of ratio scales include height and weight. Ratio scales provide a wealth of possibilities when it comes to statistical analysis. These variables can be meaningfully added, subtracted, multiplied, divided. Central tendency can be measured by mode, median, or mean. Measures of dispersion, such as standard deviation and coefficient of variation, could also be calculated from ratio scales. And so this slide just gives you some more examples of nominal, interval, ordinal ratio scales. Now let's talk about frequency distribution. A frequency distribution takes a disorganized set of scores and places them in order, usually in a table or graph, showing how many people obtained each of the scores. Scores are usually arranged in vertical columns from highest to the lowest value, and each individual test is tallied and the frequency recorded. Frequency distributions are useful in allowing examiners to see A, the entire set of scores at a glance, B, whether scores are generally high or generally low, or whether scores are concentrated in one area or spread out. Frequency distributions are also useful in comparing one person's test scores to the entire group. So let's look at using distribution tables in practice. Imagine you are an elementary school counsellor and the principal has asked you to work on study skills for all the 4th grade students who earned a 60 or below on their reading benchmark test. He provides you with the scores of all the children. The scores have not been organised in any manner, so you decide to create a frequency distribution table. Considerations for creating a distribution table. Here on the left we can see the whole array of student scores who score below a 60 on their reading benchmark, and you see they're not in any particular order whatsoever. So first of all, let's think about the range. The difference from the highest to lowest of scores is too great, so you decide to put them in groups of scores, arranging them by increments of 10 points. What do I mean by that? Well, basically, if you're going to plot all of these points in a graph, there's 60 points there. That's way too many. So you're going to have to collapse them by intervals of 10. Oh, well, you could use any measure, but intervals of 10 seems most appropriate for this particular data set. First of all, to be able to do that, we have to identify the smallest and the largest number and make sure that increments of 10 include those. So in terms of creating a frequency distribution table, I did post a link for a video demonstration on YouTube, but I think it's a really handy way of showing you how to create a frequency distribution table if you still have questions. But organizing this information in this way gives you a simple snapshot of what scores are most frequent. You might be thinking, so what? But as a school counsellor, this information is going to help you work strategically. As a school counsellor, you should always strive for efficiency. Based off this information, you decide to conduct group sessions. You may decide to place the students in groups as per their test scores. For example, we can see that there are 16 students who score between a 21 and a 30. There's 12 students who score between a 31 and 40. There's 13 students who score between a 41 and a 50. And 10 students who score between a 51 or 60. You may want to group them by ability or presumed ability level based on that particular test. However, alternatively, you might want to use heterogeneous groups and mix up the students. So you have some high performing students with some lower performing students. Hopefully that will ignite the social learning process. So now let's talk about measures of central tendency. When summarising a group of test scores, we often want to know about the typical or average performance of the group. Measures of central tendency is a single value that describes the way in which a group of data cluster around a central value. To put it in other words, it is a way to describe the centre of the data set. There are three measures of central tendency: the mean, the median, and the mode. Measures of central tendency are ways of describing a distribution based on a typical or average performance of test scores. For example, when we go out to eat, it's good to know the average price of a plate. When we shop for cars, it's important to know the average price for that particular make and model. In education, schools often recruit students based on their students earning consistently high ACT and SAT scores. So now let's talk about the mean. The mean is good for reporting the average for normal distribution. For example, my mother-in-law lives in the countryside, and most of the houses in her area cost around about $150,000. The distribution of the home price in her area forms a normal curve from lowest to highest house prices, with a majority of homes clustering in the middle range. Let's say from 120 to 180,000. 120,000 would be the low end, 180 would be the high end, and most homes cost about 150,000. The mean, therefore, is a good estimate of how much houses cost in the countryside. My best friend, however, lives in Austin, Texas. Because of the number of billionaires living in Austin, Texas, because of the number of billionaires living in the Austin area, the variation of house prices is very great. For example, although the average home costs around $300,000, the number of rich people with houses costing hundreds of millions drives up the average. When we factor in billionaires, the average home price might look at $450,000. The bell curve is negatively skewed to the right, and the mean is not a reliable indicator of how much a house costs in Austin. Now let's look at the median. The median is the middle score, or the score that divides a distribution in half. When I taught 8th grade math, I used to tell my kids that the median is the middle score. 50% of the scores will fall below the median, and 50% will fall above the median. If the scores are 4, 6, and 8, then the median is 6. With an even number of scores, such as 4, 6, 8, and 10, the sum of the two middle scores is divided by 2. So in other words, you add the two middle scores together, divide them by 2, and that's the median. In this case, the median would be 7. To determine the median of my 4th graders' test scores, I arranged them in order from highest to lowest and looked to see which score fell in the middle. Because there were an even number of scores, the two scores in the middle are 30 and 31. I added them up and divided by 2, and my answer was 30.5. Therefore, 30.5 was the median score on the reading test among the population of 4th grade students who scored below a 60. As a measure of central tendency, the median can be used with ordinal, interval, and ratio scales. The mean is The median is good for reporting averages in highly skewed distributions. Think of the homes in Austin. It would be much more helpful to know what the middle cost of a home is, as opposed to the mean, which has been negatively skewed by all the millionaires and billionaires in the area. I just have a little typo on my notes. I'm going to go and fix that while I'm on this page. Now for the last measure of central tendency, the mode. The mode is the score or numerical value that appears most frequently in a set of scores. Referring back to my student scores on the reading test, 32 was the mode, as more students earned this score than any other score. The mode is commonly used with variables that are measured at the nominal level, such as eye color. Sometimes there is bimodal or multiple modal distribution. In other words, two or more scores may appear most frequently in the distribution. If no one number occurs more frequently than another, then it's possible that there is no mode. The mode is commonly used with variables that are measured at the nominal level, but it can also provide a quick and easy measure for ordinal, interval, and ratio data. The mode is considered the most unstable measure of central tendency, however, as it easily shifts when distributions are positively or negatively skewed. Returning to our Austin example, there may be an equal number of millionaires as there are people in the very low income range, so the mode may appear artificially high or artificially low, or it may be bimodal, where one house would cost, I don't know, $100,000, whereas the other one would cost maybe $50,000. And so in that instance, it really doesn't give us a clear picture of the average home prices in Austin. So comparing the mean, median, and mode. For symmetrical distributions, the mean, median, and mode are equal. In other words, they all fall in the same spot in the middle. For other types of distributions, no single best measure of central tendency exists. Although the mean is the most common measure of central tendency, extreme scores, known as outliers, can affect it. A few extremely low scores will move the mean down, and a few extremely high scores will move the mean up, making it ill-suited for skewed distributions. In contrast, the median works better with skewed distributions because it is not impacted by outliers. The mode is the least stable statistic of central tendency. It could be erratic and not very accurate in smaller groups of scores, and is not as accurate measure, and it is not an accurate measure of central tendency in skewed distributions. So, enough on the mode, median, and mean. Let's talk about measures of variability. Whereas measures of central tendency attempt to describe a distribution based on a typical or average performance of scores, variability refers to the degree that scores are spread out and differ from one another. A distribution of test scores can have the same mean, but the scores may be scattered or dispersed either widely or narrowly around the mean. Measures of variability are statistics that describe the dispersion of scores, that is, the typical distance of scores around the mean. The range is simply the distance between the highest and the lowest number, calculated by subtracting the lowest score from the highest score. The variance is the average amount of variability in a group of scores. It is computed as the average squared deviations of values from the mean. Variance is rarely used for reporting variability in data, as it tends to yield large clunky numbers. However, it is used as a step to calculate other statistics such as ANOVA. And interestingly, the variance, the standard deviation is the standard deviation is the square root of the variance. In practical terms, the standard deviation is the average distance of a test score from the mean. It is an important statistic for interpreting the relative position of an individual within a distribution of test scores. The wider the spread of scores from the mean, the larger the standard deviation. The smaller the standard deviation, the more scores will tend to cluster around the mean. You'll need to refer to page 59 of the textbook for this section of the lesson. So, this is the formula for the standard deviation. The formula may look terrifying to the maths shy, however in reality it's a fairly straightforward calculation. In practice, researchers and practitioners are more likely to calculate the standard deviation using computer programs such as SPSS and Excel. However, it's every graduate student's right to passage to master standard deviation. So we're going to spend some time practicing calculating standard deviation, and just walk you through what some of these signs mean. So right here, this refers to the sum. The X is the amount of participants or the number of individuals or scores in a data set. The X with a line on top of it is the mean. We know that this little 2 up here means square, and then N down there means the number of participants minus 1. And we'll talk about what this minus 1 means in a minute. And of course, this over here is a symbol for standard deviation. So let's look at this from an applied perspective for a minute. Here we have 2 teachers' 3rd grade reading scores. So Mrs. Thomas and Mrs. Lopez are both 3rd grade teachers. The tables provide data on their students' reading scores on a benchmark test. We're pretending that the average class size is 6. Please humour me. I calculated the mean by adding up all the students' test scores and dividing by them 6, because there's only 6 students in the school. So we can see here that I added Maggie's through Ashley's scores, and then that gave me the sum of 381. I divided them by 6 because that's how many students there are in a class, and the mean in Miss Thomas's 3rd grade class was 63.5. whereas the mean in Miss Lopez's class was 74.1, and this is referring to their reading score on a benchmark test. So from here, let's go ahead and calculate the standard deviation of Mrs. Thomas's third grade class on their reading benchmark. So to break this down, in the first step, what I did was I got each student's score and I subtracted the mean from each student's score. And basically that's what in the first table, the column to the right, that's what this illustrates. You'll notice that some of the scores are negative. This isn't going to be an issue because in the next step where we square them, the negative times the negative cancels the negative out and it becomes a positive. A little bit tangential for right now, but okay. So in the next table, all I did was so the answer to the score take away the mean, I inputted it in the second column, and what I did was I squared so each of the answers, each of the number in the second column, I squared it, and that was the answer in the third column. And so when I had all the squared, the scores take away the means, and I squared all of those answers, I added them up. That's called the sum of the squares. In the next step, what you do for your sum of your squares, you divide it by how many students are in your n, your number of students or number of tests. In this case, the number of students is 6. So I divided my sum of squares by 6. This is also called the variance, by the way. With that number was 420.25. I then calculated the square root of the variance, and that's the standard deviation. So we can see in Miss Thomas's third grade class, the standard deviation on the reading test was 20.5. And really the best way to learn this is just to sit down and practice. It's really simple. It can get a little bit confusing when you're calculating multiple scores and you're taking the answer from the one and moving them over to the next column, or however you organize your calculations. But the math itself is very simple. Oh, I did want to say that you'll notice in my example that I did not use the n take away 1 in my calculation. That's called the Basel's correction. It's believed to give a better estimate of the true population variance of a normal distribution. But my population is not representative of a large population of third grades. It's just the total population of Mrs. Thomas's class. Don't get too fussed over this point. When you compute standard deviation in this lesson, you don't have to subtract 1 from the number of participants unless your sample is representative of a larger sample population. So I then went ahead and computed the standard deviation using the same procedure for Mrs. Lopez's third grade class. And what you can see is that her square root of her test scores was 7.6. So what does this tell us? It tells us that the majority of tests are within 7.6 points of the mean. Does this mean that Miss Lopez's, no, hold on a sec, let's just compare that to Mrs. Thomas's test scores. We can see that Mrs. Thomas's students, the standard deviation was 20.5. That's a huge variation of scores. So does that mean Mrs. Lopez teaching is more effective since her scores seem to cluster around the mean and seem to do consistently better? We can't make assumptions, and we'd need to gather more data to see if Mrs. Lopez's students are participating in a higher quality learning environment. But at this point, there might be other stuff going on in Mrs. Thomas's classroom that these scores are kind of symptomatic of. You know, why is it that one student is scoring 90 and the other student is scoring, or other students are scoring 20? Is this a consistent trend, or is this just a one-off on this particular assessment? We don't know. We need more information, but it's certainly when we see a large standard deviation on a set of scores, it raises questions about, you know, the quality of the if it's in relation to a learning assessment. It raises questions about the quality of the learning environment. So let's talk about the normal curve. The normal curve in statistics are an average distribution of values that, when plotted on a graph, resembles the shape of a bell. The curve formed by a normal distribution is called the normal curve, bell curve, normal distribution curve, or normal probability curve. Many characteristics tend to follow a normal distribution. These include biological measurements such as height, weight, and lifespan, as well as psychological measurements such as scores on intelligence tests. In a normal distribution, most values fall near the average or near the centre, with only a small percentage of values falling far out above or far below the average. For example, in a random sample of adults, most will measure between 120 centimetres, 4 foot, and 210 centimetres, 7 foot tall, with very few heights outside this range. Normal distributions generally develop when the sample size or number of observations is very large. So going back to my very small class size, it wasn't a very large sample population. So subtracting one participant wouldn't have enhanced the scores in any way. Some areas in counselling are not normally distributed, such as depression, because a relatively small number of the average population actually suffers from depression. The amount by which values vary from one another defines the shape of the normal curve. If most of the values are similar, then the normal curve is a tall and thin bell, such as in Miss Lopez's class. If there is a lot of variation among the values, then the normal curve is short and wide and bell-shaped, perhaps like the students' scores in Miss Thomas's class. One measure of the variation among values is called the standard deviation, as we've already discussed. We'll discuss the normal curve more when we discuss IQ and achievement tests in a few weeks. An important point to make is that when developing a new test, researchers strive for the scores to form a normal distribution. If they don't, it may be a sign that their sample population was not truly representative of the target population. If the bell curve is skewed in a certain direction, it's quite possible that the researchers did not include all subgroups. So now let's talk about the properties of the normal curve. And just to kind of hit the high points here, 100% of the scores fall between -3 and +3 standard deviations from the mean, with approximately 60% of all scores falling between -1 and +1 standard deviation. In regard to IQ, 68% of the population score between -1 and +1 standard deviation from the mean, which is 100. So because the standard deviation on a normal curve is 15, we can say that 60% of the population have an IQ score that falls between 85 and 115. And this next chart just illustrates a normal curve. We're actually going to be digging a bit deeper into this rich information that a normal curve can give us next week, and I'll be getting you to commit this normal curve to memory. Believe me, it will be very, very helpful in your work, especially when you get, you know, percentile scores, Stanine scores, z-test scores. You'll be able to draw you a little normal curve and be able to plot where they're at on the bell curve. So, measures of relationships. Another important statistical measure in testing involves the measurement of the relationship between variables. For example, counsellors may be interested in the relationship between depression and hours of sleep each evening. School counsellors may be concerned about the relationship between socioeconomic status and scores on the reading test. So I've lost my place a second, just bear with me. So in the next few slides, we talk about inferential statistics, primarily correlation coefficients. The most common correlation coefficient is the Pearson correlation. And then the regression. Once again, in reality, it's going to be, I highly doubt that you will be required to compute any of these statistics by hand at any point in your career as a school counsellor. So we're not going to do that today. But I did want to talk a little bit about correlation and what that means. So the strength of a correlation is indicated by the numeric value of the coefficient. A 1.00 correlation, negative or positive, indicates a perfect relationship between two variables. A 0 indicates no relationship between variables. Therefore, the closer a score is to 1, either negative or positive, the stronger the correlation. As mentioned, correlations may be negative, positive, or negative. An example of a negative correlation would be perhaps, let's see, as socioeconomic status goes down, dropout rates go up. That would be a negative correlation there. However, correlation does not imply causation. We can't say that poverty causes low reading scores. We just know there's a relationship, and we have to consider other possible factors. So I'm going to go ahead and skip to slide 37, as factor analysis is also relevant to test administration. I did want to highlight a couple more points about correlation, though. So the last set of slides highlight some basic statistical concepts pertinent to assessment. The most common measures of correlation that you'll encounter is Pearson correlation and measures of regression, as I mentioned. From correlation, we can only get an index describing the linear relationship between variables. Like, we know there's a correlation, but as I say, it's not a causation. In regression, however, we can predict the relationship between two or more variables and can use it to identify which variables X predict the outcome variable. Therefore, correlation will inform us that a household has an inverse or negative relationship with SAT scores. Regression can be used to predict an outcome between household income and likely SAT scores. So in regard to regression, well, as I said, it's unlikely that you will be actually computing regression, but it's just important to know that distinction, that regression, correlation is just, we know there's an association. With regression, it predicts. So there is a strong likelihood that a certain outcome is going to occur if a certain variable is present. And now I will just skip to the last slide, slide 37, factor analysis. actually that's incorrect, it was slide 35. So factor analysis techniques are used in test development processes as researchers compute the extent of differentiation between different constructs measured by an instrument. And this helps basically establish the construct validity of an instrument. And we'll talk about this in the upcoming weeks. And so I know that this is a lot of information to take in. And so I encourage you to read the textbook, go over the PowerPoint, look at the videos on YouTube, and then I have your learning or your discussion post this week is going to consist of 2 activities. In part 1, you're going to be creating a frequency distribution table, and then in part 2, you're going to be practice calculating the measures of central tendency and variability, which includes the mean, I think it's just the mean and the standard deviation of a set of scores, and then making some comments about what you think what these scores may mean. So, for example, in my example with Mrs. Thomas and Mrs. Lopez, we kind of get a sense that perhaps something is going on in Mrs. Lopez's classroom that that is slightly off kilter. So whether it's the students, we're concerned with the students having perhaps a learning disability, or perhaps there's a couple of gifted students in there, or is there something deficient in Mrs. Thomas's teaching methods? We don't know, but it raises questions that we're going to further investigate. Perhaps if I was a school counsellor in the school, I might go and do an observation of both teachers to see what's going on in their classroom. Of course, you have to be as most supportive and non-judgmental as possible and have that relationship there. But ultimately, we're seeing it. The outcome is this differences between the 2 classrooms. It's impacting student achievement, and so we need to do some more research. Okay, I am going to sign off now. I hope that, I know it may seem a little bit overwhelming at first, but as I say, go find yourself a quiet place. It's actually really simple, and then once you get going with calculating the standard deviation and creating your frequency distribution tables, it's a really very simple process. And you'll be really proud of yourself that you've calculated the standard deviation. Okay, well, thank you. Bye.